Hello, good people. Welcome to video one of Unit 6. Unit 6 is going to introduce us to definite integrals, which is the second part of calculus. We have differential calculus or derivative calculus, and then we have integral calculus. And so the work that we're going to do here in the first videos is going to kind of give us the foundation for what we need in terms of understanding what a definite integral does, how to read a definite integral, the notation that we use, and then how to find exact definite integral values and approximate definite integral values. So just like the derivative, there's a way to find the exact derivative value, and then there are ways to approximate it, right? And so I guess what I need you to remember is kind of keep the conceptual understanding of these two big ideas. So here we have the derivative, which was what all the fall semester was about. And the derivative at its very core is just the slope. It's a rate of change, right? It's telling me how is the function changing at any given time or any given moment of the function. Whereas the integral, let's use this color, the integral is about accumulation, and we usually think of accumulation in terms of area. So we are dealing with two very complex ideas in derivatives and integrals. However, they simplify to these two very accessible ideas of slope and area. And so we're going to start today with this section. I'm actually going to start with section 6.6 before going back to 6.1 and 6.2, because I think 6.6 gives us a good idea of what a definite integral represents. And so a definite integral represents the area bounded or between the function and the x-axis. And we're going to use this symbol right here to determine the fact that to determine the definite integral. So this is telling us we're going to find the definite integral. These numbers that are here and here are called the limits of integration. And the limits of integration tell me kind of the interval or domain where we're going to be looking at, limits of integration. What we're going to find later is the limits of integration are related to whatever this variable is. So I see this dx, that means these are x values. We might see a dy, then the limits of integration would be y values. And we'd be looking for the area that's trapped between the curve and the y-axis. So the fact that this is a function in terms of x, and I see the dx, means that these numbers in pink are x values. So this is really telling me that starting at 0 and ending at 4, the definite integral of the function f of x is 7.5. This inside part, or the function itself, is called the integrand. So we're taking the definite integral, that squiggly s, elongated s-looking symbol, of an integrand. This is called the differential, which tells me what variable I'm using. So I'm taking the integral of this function, and this is the function f of x that we're shown, from 0 to 4. And what that really means is we're looking for all of this shaded region between the function and the x-axis. And someone has found out that that area or accumulation is 7.5 exactly. Our job in the coming weeks is to figure that out as well. Once we know what the function formula is, if we're given an equation for f of x, we'll be able to do that. So what did we find? What does the definite integral represent? So interpret the integral of f of x dx from 0 to 4 equals 7.5. So what this is saying is the area accumulation between f of x and the x-axis is 7.5. That's what that means. which then tells us that if I ever ask you, or if the exam asks you to find the definite integral graphically, what we're really going to be looking for is to find the area under the curve, or I guess between the curve and the x-axis, if it's in terms of x, using geometric formulas. So if you understand what we're talking about here, then you can probably get these definite integrals fairly easily by using a little bit of geometry. So we're given the graph of g of x, and we're going to find the following. We're going to find the integral of g of x dx from -1 to 4. So I'm going to go ahead and mark that off. From -1 to 4. From -1 to 4, this whole thing finds this shaded part that I'm about to shade in. So what that integral finds, the integral of g of x dx from -1 to 4 is the area that I'm shading in. But this area that I'm shading in, very slowly, is just the area of a triangle. So if I can find the area of the triangle, I just found the definite integral value that number 1 is asking me for. So how do I find the area of a triangle? There's different ways to do it. Here's one way to do it. 1/2 base times height. Do I know the base? Sure. The base is 1, 2, 3, 4, 5 units. Do I know the height? I think I can measure that. The height is 1, 2, 3 units. And so my answer would be whatever 1/2 times 5 times 3 is, and I believe that that is 7.5. So the integral value of g of x dx based on this g of x given graph from -1 to 4 is 7.5. That's what a definite integral finds at its very core. Just like the derivative at its very core is just a slope, it's just a rate of change. At its very core, the integral is just the area under the curve, or between the curve and the x-axis, right? Now, will integrals get more complicated? Maybe. Yes. And are they going to be more useful once we find their applications? Yes. And that's where we're headed. Okay, so that takes care of that. Can we do number 2? Can we find the integral of g of x from 2 to 4? Sure. From 2 to 4, that would be from here to here. So now we're just looking for the shaded area in this little triangle there. So it's another triangle. So again, I remember that the formula is 1/2 base times height. And that's one of the formulas you have to remember from geometry. The base now is 2. The height is still 3. And so therefore, my answer is 3. The integral value of g of x dx from 2 to 4 is 3, because that's the area trapped between the curve and the x-axis. We'll do one more in this video. We'll come back and try some more. Number 3, can you find the integral of g of x dx from 2 to 10? Okay, so from 2 to 10. Well, 2 is right here. 10 is way over here. I already found this part, so I already know that that part is 3. So all I need to do now is find the area over here, and I'm good to go. So now how do I find the area in this shape? Well, there's different ways to think about it. Some people like to break this up into a little triangle, a rectangle, and then another triangle. Some people like to do it all at once and know that this is a trapezoid, and this is base 1, and this is base 2, and the height is here. But that means you have to remember the formula for the trapezoid, which we're going to use next week. So different ways to find the area. You can break it up into little pieces and then add them all together, or you can just take it as a big shape. I'm going to take it as the big shape of a trapezoid. However, I do want to remind you that I already know from 2 to 4, this is 3 plus, so from 2 to 4, I already have that area, plus I'm going to find the accumulation area here between 4 and 10. And I'm going to use the formula for a trapezoid. The formula for a trapezoid says 1/2 the height, which in this case is 2, times base 1 plus base 2. base 1, which is 1, 2, 3, plus base 2, which is 1, 2, 3, 4, 5, 6. And then that's going to give us the total area of the trapezoid. What it really is, if you look at the formula for the trapezoid, it's really telling us take the average of the bases, and multiply it times the height. You know how we find the area of a parallelogram or rectangle and say base times height? Well, here this is saying, oh, there's two different bases, right? This base is not the same length as this base. Okay, we'll take the average and then multiply it times the height. Maybe that's a better way to remember it. But I think this is how most geometry books will have it: 1/2 times height times base 1 plus base 2. And if you do that, I believe this second part will be 9 plus the original 3 gives me a total integral value of 12. So if I start at 2 and I go all the way to 10, which is what the integral is telling me to do, and find the accumulation under the curve between those two x values, my area is going to be 12. Easy, is it? We'll take a look at the next video and see how it can get a little bit tricky.